Now 8.4 is an example, is the simple geometry to just example how you solve the wave equation for the waveguide and calculate the mode. So we use the whatever the notation, the equation in 8.3. So basically now you're solving the equations are this wave equation for one scalar quantity field, either for the TMO is EZ and TEMO is the BC, but the general, the unified notation is so you have T actually Laplacian and equals gamma square operate on the function psi is 0. And this gamma square is given by 0 omega square minus k square. And basically it's the eigenvalue problem because we need to solve for gamma, what gamma will be able to find a solution psi. Then subject to boundary condition. The boundary conditions are Tm is psi 0 on the boundary. The Te is also psi positive n on the boundary is 0. Okay, so these are the equation we need to solve and the conditions. Now the rectangular waveguide is just the cross-section shape is a rectangle. So we have this is x and y. The waveguide is from 0 to A on x and 0 to B along y. So you have rectangle. And assume perfect conductor outside the boundary. So now we're solving the wave mode inside. Okay, so that's the geometry of the problem. And so the solution should be straightforward. We solved a similar thing for Laplace equation already, right? So especially the boundary condition. So for the TMO, so this is a Dirac boundary condition. So psi is 0, and with the choice of the boundary at 0 and A, you know the boundary conditions can be satisfied by summing all the sign. Right? We did that quite a few times. Psi.
Is it a 2D geometry or is there a Z component? This figure, is it a 2D geometry?
Well, this is the cross section. Z is going out. The wave propagation direction is going. The waveguide is going up, right? Infinitely long cylindrical waveguide going out. Okay, it's like a whatever you call it, a duck. Right? So this is just a C side, this is the Z component, either this is TMO, so this would be EZ, and TEMO size is BC. Right. So the solution first is for TM is easier. This is the K boundary condition. So this is to satisfy the boundary condition will be given by just like what we did before. So you have x and y, so m, n, and you can have some coefficient also if you like. Jackson. I mean, Jackson didn't actually write whatever you use, coefficient a, m, n. It doesn't matter. This is actually not needed for the eigenvalue, we'll see that. But in general, you can assign different amplitude for your mode, and then sine m by a pi x of a sine m by y over b, right? And the form we did that before. We considered it many times now. So because choosing this form at on x equals 0 boundary, obviously this is 0. But y equals 0 boundary, this is 0. X equals to a boundary, this is sine m pi. Sine m pi is always 0 if m is integer. So you sum over integer. Likewise, you sum over n is integer, but you don't include 0. M and n is 0 because if it's 0, then some sign is totally 0, and psi is 0, then everything is 0. That's just a trivial solution. So sum over n is 1 to infinity, n is 1 to infinity. Okay, but that's the form of psi, but you still need to satisfy this equation. So you substitute this back to here. Okay, yeah. So when you substitute it into here, you need the Laplacian. This is a transverse Laplacian. Transverse Laplacian is just taking the partial square partial x square plus partial square partial y square. Right? With that straightforward, because these are sign. Partial square partial x square will pull out minus m pi a square, the whole thing square. And the second derivative of the second term will pull out the minus n pi over b squared. So altogether is sum of n. And it's still the same coefficient, but you pull out the minus square bracket pi over a squared. That's for the second derivative with respect to x, but then the sum over the second derivative with respect to y. N pi b squared. And then keep the same sign function, because the second derivative will keep the sign. The first derivative will change it to cosine, and another derivative will change back to minus sign. That's why you have the minus sign. Okay, I think that's everything. Now this one plus gamma squared times this one will be 0, which means gamma squared must be equals to the negative of this, which is this plus that one. So that one implied, when you plug in the back to the wave equation, that implied gamma squared must equals to square plus square. All right, so that's the condition. So once you know that gamma only take a discrete value when m and n are from 1 to infinity, so you can give it a label, or you can say this is equal to gamma. Define that as a gamma n squared. Okay, that's straightforward, right? So assuming that you are given a omega, so arbitrary omega, just choose your frequency, and then k would be k squared would be equal to mu omega, mu epsilon omega minus gamma n squared. So this would be your wave number. Also now it's discrete. So you only take a discrete value given by this k sub mn, which is given by this gamma mn given by this. Okay, and also the cutoff is when omega is less than a certain value, then we can not have this mode. This can mn mode. The cutoff is now the omega mn. Omega mn is when this is 0. That is gamma mn divided by square root of epsilon. Okay, then now we can put this back to here. And every you take the square root, and both term has a pi square, so we take our pi, and then divided by mu square root of mu epsilon, and then the square root of m over a squared plus m over b squared. Okay, and now you can consider the lowest cutoff frequency. Obviously, from this form, the lowest one is the smallest of mn. Is both the smallest ones are 1. So this lowest cutoff is omega 1. It's just basically setting m and n equals to 1, so that becomes 1 over a squared is 1 over b squared and squared. Okay, so that and then you can figure out all the other modes. Right.
What does cutoff frequency mean?
What
does cutoff frequency mean?
Well, last time we talked about it, you forget. 8.4. Figure 8.4. You see that the k, if omega is smaller than this one, omega say whatever this omega is smaller than this one, then this is negative, right? Negative k squared is negative, means k is imaginary. If you have we assume you have the I k dependency. If it's imaginary, that changes to e to the either plus or minus, but we usually choose the decaying one because obviously the rows should not grow exponentially, so this becomes minus. Okay, if you have an imaginary part, k sub I. It damned. It means it does not propagate. You try to usually in waveguide application, you try to drive it. You have some kind of antenna. You try to drive the wave. Depends on what frequency you use. If the frequency is lower than a certain the cutoff mode, then you cannot drive the mode. The mode will not propagate, right? Because over small distance it will damn the wave. So you won't be able to excite that mode. Okay, and last time we already solved that. This omega actually is going back to this k as a function of omega. So this k becomes the square root, which in Jackson's picture, part k over basically k versus omega, but normalized. This Jackson normalized this square root of omega. It's basically divided the square root of this to the other side. Take the square root of the whole thing. And so that is the functional form is this after you define this omega mn, this of k, this one k, mu epsilon omega is just 1 minus omega squared over omega mn squared. Right. So the shape of this one is just start with this omega mn, so whatever the value, the lowest one with omega. And for large omega, right, the other way around, it's divided by this. The other way. But for large omega, so this one is 0. Go back to 1, asymptotic to 1. That's the shape of this function, right? So if omega too small, then you cannot. There's no intersection with this function, right? And you cannot find a solution that for real k that the mode is not propagating. So you need the omega greater than omega 1,1. Then the k will be this point, and you can have a real solution for k, right? And obviously, well, with this explicit solution, you can put all the other omega. The omega 1,1 is the smallest one, so the next one with omega 1,2, omega 2,1, depends on which one is larger. A is larger or 2 is larger. Like omega 2,1, this would be 2 square, right? 2 square, and then this is 1, maybe 4 over a squared, and then what b squared. The other way around, 1,2 would be 1 over a squared plus 4 over b squared, right? Then you can plot them, and it depends on which a and b and what the ratio is. Then these two may not be the same. So 2, omega 2,1. If a and b are the same, they will be the same. Then this will be the case of what we call degenerate, right? But you can have all the other mode, all the other cutoff. Right? So it depends on where your omega is. So if it is above omega 1,2 but below omega 2,1, then you have 2 modes. You can get 2 modes. Right? If you have omega is very large, then you can get many modes. Okay, that's the general situation. Is that okay? Up to you. Any more questions? All right, so now we solve for psi for this case, or for T, at least for Tm, and then we use the formula to calculate the transverse component, which is just taking gradient. Like for this case, you go back to equation 8 points. 8.33. 8.33 has 2 equations actually. For the TMO in this case, you solve for ET. Transverse component of ET. So injection is you have to keep the plus and minus, and consider K is positive. Radical gamma square that T psi. If the psi is given by this one, grad T is just the gradient of psi, which you know how to do. This is just involving just the X and Y derivative, X and Y component. So that's straightforward. So but this is taking one derivative, so it's like the partial an X component is partial X. So operate on this one. It change that to cosine and pull out the m pi over a factor in front, which is straightforward. And this gamma is the same as this gamma. And K is solving by this one. So everything you have here. And then, so you get the EX and EY component this way. And then, so once you have ET, then you can use the 8.31, 8.31 or 32, Jackson actually put it in a so-called unified. So HT is plus or minus E cos ET, and divided by this Z function. The Z function depends on whether it's Tm and TE. But Tm, Z is K over epsilon omega. Okay. For T is the other way around. It's mu omega over K. Okay. But anyway, so using this, once you have that solution, and then the eigenvalue gamma square and K square, then you can find the transverse component by taking derivative and then by this cross product. Okay, so that's TMO. And now this the rest is straightforward, so I'm quite not writing it down explicitly because just taking gradient is straightforward, right? So that TM is okay. So that yeah, that's easy. That's how Jackson is. It is in the textbook, so you can go back to the textbook. This
so
is
that is not along this here.
This is just capital Z. This is not the coordinate Z. Okay, this is just a symbol, a variable. So this equation is 8.32. This is 8.31. Okay, so we did that, and they are coming from the equations that we divide 8.23 to 25. From this you can divide this. You can divide this. I suppose I went through that last time. How you get from 8.31? How do you get 8.31 to? I mean, you can go back to 8.23 and 25, or from 8.26, which is the same because you solve 8.26 is how you so after you solve 8.23 and 25 and express the transverse component in terms of the parallel component, I mean Z component, then you get the 8.26 A and B. So either way, you can divide 8.31, but Jackson just write it in some kind of uniform notation, but with different choice of this Z variable, which is called impedance. It has the same dimension as impedance and maybe some physical meaning of this impedance, but for us, it's just a coefficient that you need to choose according to whether it's TMO and TEMO. It's just an SI thing because in SI the dimensional electric field, magnetic field are different. They are different, and they actually all four fields are different. E, B, H, and D. They're all different. But in Gaussian, they are all the same. It's just because of because the choice. I mean, this is for the TMO. This is E, electric field. Psi is electric field, and but for the TEMO, psi is the magnetic field. You can either use BZ or HZ, doesn't matter, but they are not the same dimension. Therefore, when you write down the equation, obviously you change the form change, and you have this mu and epsilon and going around. So, but anyway, you just need to use the proper equation. Okay, okay. So up to here, okay. So now we move on to TE rule. So instead of erasing everything, I put this to here to use the other side. Like that. Okay. Because it's pretty much the same, except that now this obviously does not satisfy the TEMO boundary condition because we want the derivative to be zero, not the value to be zero. The value to be zero is the derivative. This is the Neumann boundary condition. We want the derivative with the zero on the boundary, right? And the obvious choice is that instead of using sine, you use cosine, right? Because if you use cosine, then the normal derivative will give you back the sine, and then sine, the sine term, just like this, will be zero. And the normal derivatives may along x x equals 0 or x equals to a would be partial x. This is the n direction. For x equals 0, this n direction is x. At x equals to a, the n direction is minus x, right? And so on. The y equals 0, the n will be in the y direction. The y equals to b, n will be minus y direction. But either way, if you just choose your for the TE mode, you just choose sine using cosine instead of sine. Now the mn limit may change, so but we leave it open for now. So it's whatever the coefficient, and then you can, instead of using sine, use cosine. Right, and you can now explicitly check all the boundaries, like at x equals 0, and then n is partial x. N is x, so the partial n is partial x. We operate on this one, right? And so we pull out a m pi over a, actually minus m pi over a, and then times sine n pi x over a, and then substitute x equals 0, that obviously is 0. Likewise, at x equals to a, n is minus x, right? So you take the derivative, still the derivative of x, so you still have the sine term, is sine n pi. At x equals to a, you cancel a, so the sine n pi is 0 for all integer, so that means that it's 0. So likewise, you use this cosine term to satisfy the boundary condition of y equals to 0, y equals to b. Okay, so this is the correct form to satisfy the boundary condition. All right, now if we can figure out the limit. Now, the limit before is that if you cannot have m and n equals to 0, because for sine you substitute 0, the whole thing is 0, but not for cosine. Cosine you can have so if m is 0, then you get this is just 1. Likewise, n is 0, that is just 1. You still have the other factor. So all you require is that m and n cannot be both 0. If they're both 0, then it's just a constant. If psi is a constant, we get everything from, for the transverse component, we get from gradient, transverse gradient, which we give is 0. So for TE mode, psi is just the dz. So you have a psi is just a constant, means you have a uniform magnetic field, and all the transverse component is 0. So this is basically would be just a uniform magnetic field doing that thing. If you going back to substitute back to this one, because the gradient will be 0, to have gamma squared psi equals your gamma squared will be 0, right? In that case, gamma squared will be still this one, because it's still the same kind of sinusoidal function, right? But you m and n are both 0, gamma squared is 0, right? Gamma squared is 0, so but this is just it's just a uniform field that satisfy the vacuum dispersion relation k squared is mu epsilon omega squared, right? So that would be, and it won't have transverse field, right? That's not an interesting mode to consider, right? So we'll see that we'll exclude that mode. Basically, we'll exclude that mode, 0, 0 mode. right? So we say that is M is both M and N are 0 for infinity, but M N is not equal to 0, 0. Exclude this part, this mode, right? So the lowest mode will be either 1, 0 or 0, 1. Okay, and likewise, you can solve for gamma square, and the same thing happens when you take the Laplacian, transverse Laplacian, you pull out this factor, except that everything becomes cosine. But the eigenvalue is still the same. The k is still the same. K, the expression of k, the cutoff figures is still given by this equation. So everything is the same except that the lowest mode, now the lowest cutoff, is either omega 1, 0, which is we put in 1, 0 here, 1 is 0, just 1 of a squared, either pi over a, or omega 0, 1, pi b, mu epsilon, right? So which one is lowest? It depends on whether a greater than b or b greater than a. If a greater than b, obviously omega 1, 0 is greater than 0, vice versa. Okay, but this the lowest mode for the TE mode, and both will be lower than the lowest of the TMO, because TMO has both the 1 over a squared and 1 over b squared here. So this one will be greater than both of these, right? Which is pretty obvious, right? This one is greater than both of these, right? So now in this case, you are actually adding omega 0, 1, omega 1, 0, and then you still have something lower than that. And we are not, obviously, we are not including the we're not including the 0, 0 mode. For 0, 0 mode, the cutoff is actually 0. You always have that mode. But this mode is just uniform magnetic field. Right. Okay, so I guess that's all in here. Okay, is it okay? Oh yeah, I forgot this. I got this the transverse component. Well, for TE, it's slightly different. Well, you can use what Jackson did. Solve for x sub t first. For this one. So it's pretty much the same as for the TMO, you use this one. But you're solving the transverse magnetic field first. And then to solve a transverse electric field, you can use 8.31, but you probably need to do another cross product with the C unit vector to solve explicitly what E sub t is. Or you can go back to 8.23 to 25 to solve for the transverse component. So either way, there are different ways you can solve for the E sub t. Right. That is should not be difficult. Okay, what else? I think that's it. I mean, Jackson actually wrote down the TE10 mode, assuming A is larger than B, which is the lowest frequency mode, and write down the component, the transverse component, in this case, because it only has one, I mean, for omega 1, I mean, Mn is 1, 0, 1, 0. So this one will be just 1. You don't have y dependent. Everything depends only on x, right? And so this all this derivative become trivial, and you can get to 8.46 with just one coordinate dependence of just one coordinate. It just depends on x. So everything depends on x only. I mean, obviously you have c dependence in the phase in the propagation, but otherwise it only depends on x. So it has 8.46. Okay, so that's not difficult. Okay, so up to here, any question up to here? This is an example, 8.4, and so this is almost the simplest case you can think of. And another case, simple case, is instead of a rectangular cross section, you can have a circular cross section. And we'll do that a little later when we talk about the resonator, is the waveguide. The two problems are very similar. The waveguide is infinite long. To go rectangular waveguide, the cross section are the same along the z direction. Everywhere you cut, every z value you cut, the cross section is the same. But for resonator, you just put the boundary on two cross sections at two locations. So basically, you have something different. A material inside a cavity. So it's so inside you have a material with mu epsilon. Outside the boundaries are perfect conductor. Okay, so you can have a wave mode that is within this resonant cavity. So this resonant mode just basically the standing wave inside this. It's just like any cavity. So even not just electromagnetic field, you have some kind of instrument, musical instrument, that you get a standing wave inside that will give you the frequency of that, like a drum or something. Right. So that's we solve this with a circular cross section. So, but the formulation is the same in this when you solve for this transverse wave function or wave equation, and so you can have a circular resonator, but you can also use that to solve for the circular waveguide. And likewise, this rectangular cross section, this problem rectangular cross section problem, you can also consider rectangular resonator, which is a cube becomes a cube. Right? That is also easy. Right? So another simple geometry will be in homework. I think I only posed that. It's a rectangular waveguide, but you cut it in half, in the two halves. To basically make another boundary. So either you keep the lowest one or upper one, doesn't matter. You keep this part of that. And the solution will be similar to this one, except that you need to keep just the right symmetric mode. The mode with the correct symmetry, such that the boundary condition is also satisfied along this new boundary, right? And for that case, there is a triangular waveguide. You need for that to work. It basically is whatever what we call that kind of boundary with the two distance sides are the same. You can do that, right?